Okay, I want to thank the organizer for inviting me here to give to talk about our work. If you notice that I changed slightly the title of the topic, it's now called Discrete Temporal Models for Evolving Graphs, because I realized that I only have 20 minutes to present the work, so I need to scale down the material I want to present to you. So this is going to be a part of the thing I want to present originally. But fortunately, I'm after Edo and Mike, so you are now fairly familiar with the context of this talk, which is about analyzing networks of various kinds, and I don't think I need to motivate that further. But I want to point you to a particular phenomenon in network. So for those of you who might be following the presidential campaign in the United States, especially if you follow the pattern of those superdelegates who are switching their support for their candidates, you may notice that if we are talking about a network, especially a social network, we're really talking about a dynamic phenomenon. The network itself is changing all the time. Like here, I'm showing you a graph showing the party polarity over the past 100 years. And for those of you who are interested in biology, this phenomenon is even more striking. So for example, when we were measuring microarray expression data from biological entities, usually we are really talking about a time course over a specific physiological processes. And in case of micro data, like imaging of biological patterns, and again, you want to take a movie, which is again, a temporal process. And sometimes pathologists take tissue samples over the course of a cancer development, and all these data are actually produced perhaps not by a single network, but by a time-specific network which have different topology over different time points. So this important phenomenon wasn't really carefully studied in current literature. Mostly people do the following two things. They either have this data and ignore their timestamps and collapse them and assuming that they are IID samples from some hidden networks, and then infer a network like this using fancy graph estimation technology. Or sometimes they estimate the so-called dynamic Bayesian networks, which is nothing more than a stationary transition model, which is based on a time-invariant network structure. So what we really want in some of the contexts I described might be the following. We want to explicitly model the phenomenon that we have a sequence of networks over discrete time points in the simplest case, and where the topology of the network itself is changing over time, and maybe they are not changing dramatically, but having a smooth fashion. And then at each time point, you may have time-specific expression of genes or other covariates. And sometimes the condition can be relaxed a little bit. For example, you may say the network are more stable than just time-specific variation. Maybe they vary over every epochs, and then within each epoch, you have multiple samples of the gene expression data or other kinds of data. But anyway, in any of these cases, if you want to really estimate time-specific network naively, it's going to be a mission impossible because you really don't have enough data to do such estimation. Okay, in this case, for example, you have maybe 5 samples, and in the extreme case, you have 1 sample to estimate your network, which is a pretty hard problem. So the goal of this talk is to present some of the recent work we did to hopefully come up with a statistical framework which allow us to do tasks like time-specific estimation of networks by putting up a specific model to describe how graphs evolve over time. So here is the context of our talk. We assume that we, at the beginning, observe a sequence of networks at discrete time points. And we also, for simplicity, assume that the model is going to describe the evolution of network topology over a fixed set of nodes. Therefore, the size of the graph is not changing. So to really put up this problem, we need to begin with a way to write down the joint distribution of the sequence of networks. And based on the usual tricks statisticians like to do, we want to start with a simplifying Markovian assumption to break this joint distribution into a product of translation probability models. And therefore, we can write down the joint as a product of transitioning probability from one network to the network in the next time point. Now the problem reduced to how can we parameterize this conditional likelihood model. And fortunately, Edo already gave a pretty good introduction of the machinery we had so far. We have, for example, the P-star model, also known as the exponential random graph model, which tells us how to write down the distribution of a random graph using this log linear model built on graph statistics. And here is an example of such graph statistics. You can count the number of edges, the number of triangles and toothsets and so on, and weighted them accordingly. I write down this joint distribution like this. And you can use a maximum likelihood estimator to really estimate these parameters based on data using various different methods, such as the MCMC sampling method. So you want to build on this technique by a very simple extension. For example, what if I want to write down the one-step transition model of a pair of networks using also an exponential random graph model, but this time the potential function of this random graph model is built across two graphs rather than only a single graph, right? So that's a natural idea. And now the problem reduced to how can we choose the right type of statistic to parameterize this model. And here we again take the liberty of doing a further simplification. We want to build what we call as a factorizable temporal potentials, which can be best displayed by a few examples. So here, for example, we can call the potential function like this, in the following fashion. First of all, one of the possible potential function could be what we know as a graph continuity function, where you want to penalize dramatic changes in network topology over time. And this equation actually says that. And you may notice that this is a potential function which is sum over all edges in the next graph. Therefore, when they enter the exponent part of this model, they will be factorizable as a product over each edges. And then there can be other potential functions which capture the property of reciprocity, transitivity, density, and so forth, which are just simple common sense behavior you may imagine for a network and you may want to enforce for a network to involve. So after design such potential functions, you can put them down, weighted them accordingly, and then build a build a first order graph transition model using a log linear model like this. And that's our building block of the model. Of course, you can design fancier graph transition potentials based on your common sense. You may be able to design, for example, higher order graph statistics based on graph motifs, or maybe some other sociological effects, such as the hub likes to be speaking loudly, and the k-clicks and triangles, the way they evolve, and so on and so forth. And the nice semantics of this model is that you can essentially plug in all these building blocks and slightly increase the number of parameters to accommodate all this graph property. And that didn't really increase the difficulty in estimating or inferring about this model. For example, you can use a maximum likelihood estimator to learn the parameters from data. And here I just give you, some high-level derivations on how this can be done. Basically, you write down the likelihood of the data, and you take a derivative of the likelihood of the log likelihood with respect to each parameter. And by doing that, you have to compute the expectation of the sufficient statistics under the original model, and that can be approximated by a Markov-Chain Carlo sampling scheme. Or in some cases, you can even get an exact estimate, a closed form estimate of this statistic if you assume a certain specific design of the model. And just to assure you this is actually working, here is an example. We simulated a bunch of graph sequences, use this set of parameter, and we can estimate the parameter back. And you can see the number here is not too much different from the original one. So we have the model. And now we want to ask a more delicate question. Are these models good enough to describe actual network you observe in the data? Because recently it came to our attention that some statisticians, such as Mark Hancock from UW, observed that for certain exponential graph models, they have this very nasty property called degeneracy, which means that this distribution of the graph is somehow ill-specified in a sense that they put most of the probability mass to a very tiny subspace of the graph topology. Therefore, you can really not use this model to describe the actual graph you see. And here is a graph to illustrate that. So we plotted, for example, the probability mass of a specifically parameterized ergon model. And here, to illustrate the density function, I have these two axes. One is counting the number of edges in the graph, and here is the number of triangles in the graph. And the corner here roughly correspond to a complete graph. You have a lot of edges and a lot of triangles, and here it's almost like an empty graph. And you can notice that the mass are really concentrated in these places, and all these other graphs gets almost zero probability mass. And more specifically, this prominence is pretty prevalent in ergon model. And here I show you a graph which shows you a whole space of the way to specify the edge and the triangle potential weights. And you can see that in most of the area in this parameter space, you have very low entropy of the distribution, means that the distribution is almost deterministic, meaning that their mass is concentrated on just a small set of graphs. And there are some spaces, some ways of parameterizing them, which gives you a benign distribution. So if we have a model like this, then chances are you cannot use this model to describe the data. And in fact, Mark showed that you cannot even estimate such model from data, because your observed sufficient statistics may well lie outside of the convex hull of the realizable sufficient statistics, which means that once you estimate a parameter from the data and you simulate the graph from this model, you get nothing similar to what the model you actually, what network you use to estimate the parameter. So this is a bad phenomenon. I want to ask whether this phenomenon also exists in the Turgon model. And luckily, we find that we can actually prove a theorem which says that for a certain type of Turgon model, they are non-degenerate. And here I give you an equation to basically guarantee you such phenomenon, which I don't have time to explain. But essentially, you can lower bound the entropy of the distribution of the graph by some parameters, which is a function of the sufficient statistic weight in the graph. And here is a graph showing you that, for example, here is the space of the parameters that can be used to parameterize the Turgon model. And you can see that overall, the entropy is pretty smoothly distributed over the entire space. So that's kind of a comforting effect. Okay, now we have the model, and we can ask what kind of utility this model can provide. And certainly, you can do hypothesis testing. For example, you can assume the graph is evolving in a certain way. And then you have a null hypothesis, which is describing something you don't believe in. And then based on this model, you can write down the likelihood and do a likelihood ratio test, right? Of course, there are difficulties in writing down the p-value of the log odds, but that can be somehow solved by a bootstrap strategy where you can sample the graphs. And there are also ways to use this model to do data exploration. For example, if your graph nodes has hidden labels, you can use this strategy or this framework to estimate a posterior distribution of the graph labels. And here I want to follow up the story I began with to use this model to learn, for example, how we can have time-specific graphs. So here's the context again. We have a time series of, say, node attributes, such as gene expressions. And we want to estimate these time-specific networks. And again, the cover story will be you have a hidden Markov model over the graph space where you have this chain of graphs evolving over time. But these nodes are living in a very high-dimensional space, which contains all possible topologies of a graph of a fixed set of nodes. And then you have anywhere from one to a couple of observations at each time slices. And to formulate the inference problem, we need to provide a transition model over the hidden evolving graphs, which I already described. And then you also need to have an emission model to give rise to the likelihood function of the observation given the hidden graphs. And I just want to have you two slices to give you an idea about how I specify that. So the transition model will use some of the simple statistics that I described, such as density stability, continuity, transitivity, and so on and so forth. And then you can write down a temporal transition model like this. And for the emission model, you can essentially do the same thing. You can also use an exponential random graph model, which incorporates both the graph topology and also the node attributes, and maybe some other parameterization to guide the direction of influences in such context. For example, in here, I suppose I want to enforce a bias such that when the two nodes are connected by a certain edge, they should be either correlated or anti-correlated, depending on how I parameterize or specify this hidden switching parameter. Or if there isn't an edge between the pair of nodes, there should be no correlations whatsoever among them. So you can write down such prior knowledge using some specific potential functions like this. And then we have the full model. And now the task leaves us is how to do inference over the hidden variables. It turns out that writing down the model isn't very difficult. It takes us couple of weeks to come up with the model, but then we spent more than a year to actually come up with efficient or maybe plausible inference algorithm. And I show you two of our products. One is actually published, but actually not very much working. The other is unpublished, but it is actually working. And I'm hoping that the second one will be published soon. So the first inference algorithm is, again, statisticians, the first thing statisticians ask will be, how about doing a Gibbs sampling? Okay, and we did that. So it turns out that doing Gibbs sampling for this model is extremely non-trivial because your state space is just too huge for you to visit exhaustively. For example, suppose I want to sample the posterior distribution of a particular graph, given its Markov blanket. Then it turns out that I need to compute the log odds in the following form, where each of term contains a ratio of the partition function dependent on changing graphs. That means whenever you change the graph topology by a single edge, you need to recompute the partition function conditioned on that graph. And that is actually quite difficult. We didn't really come up with a good strategy of computing that. So we actually just want to test the feasibility of this model, and therefore we implement the exact inference technology. We do enumeration to compute the graph partition function, and it worked for a graph of about 20 nodes. And with that, we actually tried to assess whether using the Turgen model is at all a good idea for inferring time-specific networks. And here is a comparison of our algorithm to a study case. So here we simulated a sequence of networks and their node attributes based on a two-parameter simulation scheme. One parameter is the theta, which can be roughly understood as a way to control how dramatically graph evolve over time. And the other parameter is the eta, which can be understood as a parameter to control how inconsistent your node attribute is compared to the graph topology. And you can imagine that the bigger these two values are, the more difficult the problem is, because you see more and more dramatic involvement and more inconsistency between the graph topology and the observation. And we compared 3 different strategies of inferring graph topology. One is, of course, our Turgen model, and the other is what we call a ground truth, because you simulate the graphs, therefore you know actual time-specific graphs, right? And suppose you don't have a model to do time-specific inference, but you only have the assumption of inferring one graph. What the best you can get? Well, you collapse all the true graphs and get a single graph, and that's the ground truth in here. And in here, we just ignore the time evolution elements and use the node attributes to infer a single graph out of it. So this is the inferred single graph, this is a true single graph, and this is the time evolving graph. And you can see that we see a nice dominance of the Turgen model over the other technique under a wide range of simulation parameterization. And here is just a picture for fun. We actually applied this model to a network that is small enough, which is actually below 20 nodes, so that we can see something happening. And this is a result published in an early paper on a subnetwork in the species of Drosophila, and they show some graph topology over gene regulation, which we don't actually want to discuss at this point. But here is a sequence of graphs we inferred, and you can see there are some similarity overall of this collection of graphs compared to the steady one, but you'll see some interesting dynamic behavior of the graph. So this method is essentially the philosophy is working in a sense, but as I said, it is not very scalable, and we can only handle a graph of about 20 nodes. So we were very serious about that because the data we actually had in hand has at least 5,000 nodes, if not more. So we want to have a scalable technology, and here we want to do something differently. So if you forget about temporal semantics and estimate just a discrete or continuous graph from node attributes, I guess we have many methodologies available. And I think yesterday some speakers talked about this graphical Lassau technique, which can give us a sparse estimate of the graph based on node attributes. Now suppose we want to apply this technique to a temporal domain, what can be the possible extension? Well, first we have to assume that the graph is not continuously weighted, but also they should be evolving in a possibly smooth fashion so that their weights are not changing over time. Okay, so how to capitalize this concept in an inference algorithm? Well, we come up with an idea which use exactly this technique, but add a penalty function which is to enforce smoothly evolving parameters over the temporal space, which can be understood from this cost function. So we have the usual, by the way, we are interested in this case a discrete graph, so we use a L1 regularized logistic regression rather than the graphical lasso, but the whole principle is very similar. So we have this cost function for time-specific graphs, and we have this shrinkage function, which is to enforce sparsity in the estimated graph. But then for every pair of graph weights, we have this temporal difference penalty, which is to enforce that the graph weights on each edge are not changing dramatically over time. And we have different ways of penalizing this, such as using a L1 penalty, a L2 penalty, or a square of the L2 penalty, and so on and so forth. And this whole cost problem can be rewritten as a constraint optimization problem using standard technique, and then you can use some standard solver to solve the problem. And without wasting more time, I just give you 2 more slides to show the results. So here we actually compared, again, our smooth temporal graphical lasso method to other techniques such as a steady graph estimating graph method, and also some other similar technique using different penalty function, such as the L1 plus L1 and L1 plus L2. And the first L1 corresponds to the shrinkage of graph weights. The second one is corresponding to the smoothing function over time. And you can see that this particular shrinkage function, okay, L1 plus L1 is doing quite well in various different experimental settings, which I don't really have time to explain in detail, but we can discuss after hour. And then again, things, beyond simulation, we don't really have a ground truth for any network in real world. We just want to play some fun and apply our technique to a different data set. This time not biology, but the social science. So machine learning people likes to analyze the paper from the NIPS conference, which is one of our major conferences. And the cool thing about that is that there are many authors involved, which are all friends of us, so we can make fun of each other. So here we have this network, which is consisting of not only author names, but also keywords appeared in the network. And it is a network with a few thousand nodes. And we just want to present the data to this algorithm and let the algorithm to infer time-specific network. And here I show you 4 times snapshots of this network. This is a network starting from 1987 to 1988. And if you inspect carefully by looking at the Markov blanket of each keyword, you may notice that there is a certain degree of continuity over the network. Especially in here, you can actually see that, for example, this particular word called approximation has roughly the same Markov blanket in time-adjacent time points. Okay, I'm going to be over. And then there are certain patterns indicating certain authors likes to be using certain words or collaborating with certain other co-authors and so on and so forth. Okay, so that's the end of the talk. I basically presented a new class of stochastic models for dynamic network analysis. And we have a number of problems unsolved, and I want comments and help from all of you. And also we are actively searching for solutions. First is, how do we really approximate the partition function in this kind of model for large graphs so that we can analyze in really big network data. And also, we just started to investigate statistical guarantees and sample complexity of our estimation and inference procedure. And so far, we've been only able to prove very weak results, and we want to have a better opinion and suggestions on it. Okay, that's the end of my talk.
I would suggest actually we take questions offline, otherwise we're going to run out of time for the coffee break. So let's thank all the speakers from that session once more, and you'll see you back in 15 minutes.